In this video we're going to have a first look at Bayesian statistics. Bayesian statistics are usually more fun than frequent test statistics, the statistics that we usually do. And especially in policy analyses, the Bayesian result is usually more interesting than the frequent test result. Yeah, so for instance, in policy, it's usually more important to know that the parameter, let's say the effect of a subsidy or something, is bigger than 1, say, instead of testing whether the parameter is significantly different from 0. So to have a first very simple example of Bayesian statistics, we look at this idea of a population. Yeah, let's say there are 10,000 people in the population. As you will see, if you do the math by hand, actually this population is totally irrelevant, but it helps you to sort of get into things if you can count numbers. Yeah, so the only reason why we use population here is for that reason. It's actually totally irrelevant for the things that we do. So we have a population of 10,000 individuals, and we know that 1 out of 1,000 of these people are vampires. Now, a test has been developed which can test whether somebody is a vampire or not. And the probability that this test is positive, given that you're testing it on a vampire, yes, so the test gives a positive result, conditional on the test being applied to a vampire, is 95%, so it's pretty accurate. And the false positive, so the probability that the test is positive given that I'm testing a human, yeah, so not a vampire, that is only 1%, yeah, so 1 out of 100. So the test is actually pretty good. Given that it's a vampire, there's a 95% probability that I will spot that it's a vampire, yeah, so that the test will turn out positive. If it's a human, there's only 1% probability that the test will incorrectly suggest that this human is a vampire. So then we can calculate the total number of vampires in the population, which is simply the fraction, the probability of vampires times the population. And the number of humans in the population is the total population minus the number of vampires. Yeah, so we can run this code, which was already given in the notebook. So now the next step is, I have somebody in front of me. I've done the test, and the test came out positive. And the question is now, should I panic? Yeah, so there's somebody stood in front of me, I applied the test, and the test says this person is a vampire. Yeah, so there's a positive test. And given the accuracy of the test, you may think that it's actually highly likely that the person in front of you is a vampire. Yeah, so to calculate what this probability is, we're actually going to use Bayes' rule. I'm going to write down the equation in a second, but first let's simply use our intuition. So what is the number of positive vampires in the population? Yeah, so these are vampires that will test positive if I use the test. So that is the probability of a positive test given that it's a vampire times the number of vampires in the population. And what is the number of positive positive humans in the population? That's the probability that I have a positive test on a human times the number of humans. So now the thing that I want to know is, what is the probability that someone is a vampire conditional on a positive test? Yeah, so this probability is actually the number of positive vampires divided by everybody who's positive. Yeah, so that's positive humans plus positive vampires. Yeah, so when I run this, it turns out that this probability is actually about 8%. Yeah, so even though this person has tested positive and tests are pretty accurate, it's actually highly unlikely that the person standing in front of me who had this positive test is a vampire. And this result may be sort of surprising at first sight, but of course the reason why it happens, the reason why it happens is that the number of positive vampires is basically very low. On a population of 10,000, there are only 9.5 positive vampires, yeah, because the number of vampires is basically very low in this population. Yeah, so although the test is positive, it is still very unlikely that the person standing in front of me is actually a vampire. Yeah, so what we use here is what's called Bayes equation. So let's use a bit of LaTeX. Begin equation. Yeah, so Bayes equation basically says the probability that we have A conditional on B is the probability that we have A and B divided by the probability of B. Oops. Yeah, so oops. So in our case, it was the probability that I have a vampire divided by the probability, conditional on the fact that the person is positive, had a positive test. Yeah, so there's a probability that somebody is a vampire and has a positive test. Yeah, so that's what we did here. So here we have the number of positive vampires. And we divide by the probability of B, so in our case the probability that somebody is positive, and that is the sum of positive humans and positive vampires. Yeah, so this is Bayes equation. And the way we're going to use Bayes equation in the analysis is basically as follows. So what we're going to be interested in is the probability distribution of my parameter, or parameters for that matter, given that I have some data. And that's going to be equal to the probability, and I'm going to apply Bayes equation now again on the, so there's a probability on theta and data, which I can also write as the probability of conditional on theta times the probability of theta divided by the probability of my data. Yeah, so this is Bayes equation in the way that we're going to apply it in a second. So we're going to say that the probability for the parameter theta, so the likelihood of the, well, the probability is actually, I'll come back to this in a second. So the probability of the of particular values for the parameter or parameters, this could be a vector theta, conditional on the data, is equal to the likelihood, so there's a probability of the data conditional on the parameter value theta, times the probability distribution of theta. Yeah, so this is going to be called the prior distribution, P of theta, divided by all the different ways, so all the different parameter values that can actually generate the data. Yeah, so it's this equation that we're going to use in a second in an example to see how this works, how we actually get from a prior distribution to a posterior distribution.